That's why I not asked you to be switch on your video also. There's a lot
Okay.
of problems. Let's
Okay.
see. There's no power supply because that's the problem.
Oh.
Okay. Anyway, see, now I'm just talking about the radiation pattern. Okay, it might be slightly confusing. Okay, now assuming this antenna is nothing but a torch, if this what you call the center of the torch or bore sight is pointing towards the receiver, definitely it's going to pick up quite a bit of light. Okay. But the moment the torch is rotated away from this axis, definitely you're going to see less light. So that's what is happening. Okay. So instead of two ways we can represent this radiation pattern. One is using the polar coordinates, in which the concentric circles are the strength of the signal or power of the signal. So you'll have concentric circles. The last circle being the maximum power. So at a distance d, what is the maximum power? So you will be getting some maximum power, which we had seen in the previous classes, how to calculate what is the received power. When exactly the bore sight is aligned to the receiver, you're going to get maximum power. Now all these concentric circles after the first one is nothing but reduction by 1 dB. So each concentric circle represents 1 dB reduction. So this is 0 dB. The next one will be -1, -2, then -3, so on and so forth. Now, because you're free to rotate this antenna, for each angle, you can start plotting your power. So you plot your power like this. So you plot points with respect to each angle, what is the power you received. Okay. So it will mostly be symmetrical. Then join all these points. So that is going to give you the radiation pattern. Okay. Now that is one way of representing, that is polar method. The other way is using normal Cartesian coordinates, in which the same information is now represented in this way, like the y-axis is power and x-axis is angle. So you plot from 0 degrees, 0, 90 and so on and so forth up to 180. And here it is going to be the reverse direction, -90, -180. So when you are taking the reading for 0 degrees, that is exact alignment between the transmitter and receiver. That is, the antenna is looking exactly at the receiver. Then you are going to get maximum power. So you note down that maximum power. Then you have the scale of half power. That is, half is 0.5. So if you take 10 log 0.5, you're going to get that -3 dB. That's how you get this -3 dB. So you plot 0 dB, -3 dB, -6, and so on and so forth, -10, like that. So corresponding to each uh, reading, now you can plot your power. So it will be something like this. The radiation pattern is represented like this. Previous class I asked one question. Uh, why do you get something at the back side also? Any reason, Sanita, you can think of? Or just a layman's explanation? Let us say there is a building, okay? and you have put a floodlight. Okay, there is a floodlight, and you are standing just in line with the building. Probably it's night time. Okay, so that probably you'll not see much, but uh, definitely there will be a faint glow, isn't it? You can at least feel that there is some light behind the building. So similarly, in an antenna, though we assume it to be a perfect reflector, which is going to give only in the forward direction, definitely there will be some leakage that will come in the backward direction. So the forward one is called the front lobe or the main lobe, and this is called the back lobe. In addition to this, okay, my question was, is it desirable to have both main lobe and back lobe? Uh, what do you think is the answer? What will be your answer? I think I asked you in last class. You know, Sarup, I don't remember. Okay, I'll lead you to the answer. Suppose this antenna is for a radar. What would you, how would you like the back lobe to be?
Sir, same as globe.
Same, equal.
Yes, sir.
Okay, then what's going to happen is, okay, how many of you disagree with, anyone disagrees with Sarup? This is the radar screen and this is the center. Sarup says that both should be equal.
Sir, range will decrease, sir, but we will have coverage 360 at optics.
No, what is, yeah, someone, Raghavendra, Sanjay? Sarup says coverage will be more for a radar, but coverage might be less, but what he's trying to say is, okay, power radiated might be less in one direction, but he's looking at two different directions simultaneously. So what will happen on the radar scope?
Sir, it might give wrong information.
Yeah, so what's going to happen is, let us say the antenna is pointing at 45 degrees, okay, and we have a aircraft which is approaching in this direction, 45 degrees northeast, okay, it's coming from this direction, you'll see a blip, okay. The same thing, if there is a back lobe and an aircraft is approaching from southwest, okay, he is coming actually from this direction, but it will be seen as another blip coming in the northeast direction, isn't it? So you are actually confusing the radar now. So for radar applications, definitely the back lobe is not a desirable feature. You would like to have it as less as possible. Same thing applies for localizer. Okay, localizer you want beam. This is your touchdown, and you're giving an information like this, so that the aircraft can go and align itself and come to the touchdown point. What happens if this localizer is going to give another back lobe like this? And if, as such, the weather you use instrument landing system only when the weather is bad, this fellow might mistake this to be the approach, and aircraft can even land on this backload, which means he's going to get into problems. Getting it? So depending on your application, this backload has to be minimum. Whenever you have directional applications, you would like to have minimum backflows. It's again same like your car headlight. You want all the light to go forward. You don't want anything to come into the passenger compartment. Uh, Similar to that, directional antennas should have minimum backflows. Okay. Now, can you think of any application where you would like to have backlobes?
Sir, radio stations.
Yeah, very good. Because, like, let us say we are having HF communication, and this is the ionosphere. You have an antenna which is having a forward lobe like this. So you have a coverage going like this. It also has a back lobe which is equal. So you cover this area also. So this complete length you will be able to cover. So broadcasting and all, there is no issues. You really don't worry about the back lobes. In fact, it might be even a preferable thing if you don't have, if you have equal front and back lobes. Okay. And okay, this is one thing. Okay. Now, are you people getting the idea of this radiation pattern? So what they generally do is whenever they design a antenna, they have this field testing stations. Near to Bangalore also they are having one. So they mount this antenna on a pedestal which can be rotated like this, and they will have field monitors. Uh, Either you rotate this antenna or you just go around taking all the readings, whichever way is comfortable to you, and then see whether, like your control systems, antennas performance also can be simulated. Okay, so before you make an antenna, you can always simulate the radiation pattern. But after manufacturing, there will be so many issues. So you finally you depend on field measurements to see the radiation pattern. Then there is another definition. So you take this 3 dB point, you bring it down. This angle is called as the half power beam width. It just says that after this angle, you are going to have half power only, and that's going to be the beam width of it. Similarly, now because of back lobes, you will be having something like this also. In addition to back lobes and front lobes, something very undesirable happens. That is called the side lobes. At least back lobes, you know it's 180 degrees out. Side lobes are something like this. Suppose this is the main beam and you have a back lobe. Side lobes will occur in different orientations. So you will have unnecessary lobes like this. And this is what is used for electronic jamming. If you know the radiation pattern of the radar, what you do is you turn on your jammer not when the main lobe is pointing at you, but when the side lobes are pointing at you. So effectively, you can actually sneak into the radar using the side lobe jamming. And this was what was used by the Israelis in there's a famous Israel-Egypt war. I think it lasted for 11 days or something. And Egyptians had all these Russian radars. Israelis were able to during peacetime itself they were able to measure the radiation pattern of these radars, and they used the side lobes to sneak into the missile sites. So it's a very undesirable thing, back lobes and side lobes in radar applications. Okay. This is what I was telling. So half power beam width. Okay. Just minus 3 dB line. Then next, find out what angle it's going to make. So this similarly, some radars, some antennas, they talk about beam width between first null. So null is almost zero. Okay, you don't have anything, no radiation coming in that direction. And then, of course, you will have the back lobe, first side lobe, second side lobe, so on and so forth. The problem with antennas is more directive you make, more side lobes will get generated. So it's something it's a compromise. Okay. What I mean is, suppose I have an antenna which is which is having a very broad beam width. Okay. So the side lobes will be very small. But the moment I make the directivity very high, suppose I make the beam width also very narrow, this will result in large number of side lobes. So that's like aircraft design, antenna design also is a compromise between all these things. You just remember that side lobes and directivity, they don't go with each other. Yeah. Any doubts on this radiation pattern?
Sir, back lobe starts at 130 degree or something.
Ah, it's a lobe, no? So it's not exactly 180. Okay. So it starts much earlier. Like fringes of a building, when you see the light, no, it's not exactly at the edge, slightly away itself. You start getting it. Okay. Then we talked about antenna gain. It's not that it's getting power from nowhere. Uh, what is radiated in 180 degrees now gets concentrated on a particular direction. So it's always gain for a particular direction. Okay, that's what it means. Okay, then we talked about dipoles. A version of it is called folded dipole. Uh, so here you just this is the one you see on all air traffic controls. Okay. Next time when you go to an airport, you can just see on the ATC, you'll have all this folded dipoles. Just the pipes bent like in this form. And advantage being this particular antenna impedance is 300 ohms and free space impedance is 373 ohms. So it's much closer to the impedance of free space. And not only that, its bandwidth is also very high. We have very good bandwidth for folded dipoles. Okay, so you'll find this folded dipoles quite often. When it comes to aircrafts, we can't have the luxury of lambda by 2. So we use lambda by 4 antennas mostly, and that is called Marconi antenna. So instead of lambda by 2, we go for lambda by 4, but try to achieve the radiation, the performance of lambda by 2. And that is done by using something called as mirroring. So what you do is, I told you coaxial has two conductors, one in the center, the other one is the sheath. So the sheath you ground it properly and then extend lot of wires, copper wires on all directions. So this acts like a mirror and it's as if there are two lambda by 4 uh, antennas. Okay, so it's equivalent to lambda by 2 antenna. Of course, there are issues. It's no Earth is going to be a perfect mirror. So definitely the radiation is not going to be as good as lambda by 2. But okay, it's better than having a lambda by 2 antennas. That's why on the aircraft, you will find that all these antennas are projecting like this. The fuselage acts as if it's a uh, Earth, okay, Earth with a perfect shield. Of course, if it is metallic, it's going to be a perfect shield. So all antennas, either at the bottom or down, will be just projecting like this on the aircraft, and they're all Marconi antennas. And these radial wires, which are laid horizontally, are called counterpoise. So the antenna, so you have counterpoise running around in all directions. So the radiation pattern for lambda by 4 and lambda by 2 antenna was a figure of 8. Now definitely you can't have, this is for lambda by 2 antenna. Definitely you can't have a figure of 8, but instead you have this sort of lobe pattern for lambda by 4 antennas. Then we talked about directivity last time itself. So okay, this is a directional antenna in which you have the main lobe and then you have this side lobes. Generally, what they do is whenever they are drawing the radiation pattern, they'll make two radiation patterns. One is for the horizontal section, the other one is for the vertical section. So, assuming that you cut this lobe pattern, three-dimensional pattern like this, okay. So what you see, that cross section is represented in the horizontal radiation pattern. Now you can do the same cut on the other side also, other other plane rather. Then you will see the vertical radiation pattern. So you'll find two patterns because every time drawing a three-dimensional figure is not possible. So you will have two radiation patterns for each antenna. Okay. They were all simple antennas which had uh, not much of directivity. So, if you want to improve directivity, you will have to go for something called as array antenna. Array is nothing but the literal meaning is more than one. Okay, and these antennas can give directivity in two different planes. Like suppose even if you have an antenna like this pointing in this direction, you can have a low pattern which is going from the end. That's why it's called end fire. You can even get a low pattern that will be quite surprising for you on the at a angle 180 degrees also, 90 degrees. That is called broadside. So this end fire and broadside are terms which are actually used in ships. So you have a ship. So this side is called the broadside. Okay. Because its length is broad and this is called the end fire. So they are basically naval terms. Then you have something called as parasite or driven that I'll tell you what it is. So array antennas, basic purpose is it improves the directivity. It is much better than your just lambda by 4 antennas or lambda by 2 antennas. Okay. When we talk about parasitic arrays, it's going to have more than one element. The one which is connected to the transmitter through the transmission line is called the driven element. and all other elements are called parasitic elements. And the most popular parasitic array is Yagi antenna. Older generation aircrafts all use this Yagi antenna. The radars, in fact, used Yagi antennas. So how it looks like is, see, uh, it's not just one lambda by 4. Okay, you will find number of arrays. So, but nowadays there are other techniques to get the directivity. Instead of normally go for a dish mounted on into the radome itself. But older generation they use this Yagi antennas. Even now you will find a lot of aviation equipment with this sort of Yagi antenna. Okay, so how it actually works? So you have the orange one is the driven element. This is connected to the transmitter. Directly it receives power and starts generating the electromagnetic fields. Then you will have something at the back because directivity means in one direction only. The backside one is called the reflector. It is similar to your torch, which has a reflector behind the bulb. The one in the front is called the director. So this one is the director. More the number of directors, more better will be the directivity of the Yagi antenna. And this reflector will be greater than lambda by 2. And this will be shorter than lambda by 2. So if you look at the plan view, it's going to be something like this. Let us say this is the reflector. Then you have the driven element. Then you will have lot of directors like this. And you are interested in directivity in this direction. Reflector, director, and parasitic element, there is a driven element, and then these are all directors. More the number of directors, better is the directivity of the antenna. Okay. Now in ILS, uh, can you guess which equipment will be having this Yagi Uda antenna? Yagi Uda is a refinement of Yagi. Actually, they're all Japanese guys who initially came out with these things. It's open to the class. Okay, anyone can guess. Okay, I'll just give you a hint. Uh, the application requires a pencil beam, one single pencil beam. Sanjay, any guesses?
No, sir.
See, my requirement is to generate one single pencil beam, a very narrow beam, right? A pencil beam is a narrow beam. Which equipment and instrument landing system will use an Yagi antenna for that? And Yagi antennas are going to give a very narrow pencil beams.
Marker beacon, sir.
Good. Because uh, let us say this is a touchdown and you're landing like this. And marker beacons are nothing but they are just at single point, you want these beams to go up. You don't want it to flare up like this, right? You don't want a radiation pattern like this. You want a highly narrow, uh, a very narrow beam to be generated. So all these marker beacons, they'll be using Yagi-Uda antennas. Okay, good. And what you people see on your rooftops is nowadays dish antenna. Okay, and you'll find that inside aircrafts also. Okay. Before we conclude this antenna portion, uh, present generation aircraft. Okay, I'll just ask the class. Let's see how much interest you're taking in aviation. What is the main difference between LCA present version and Mark 1A? Recently, the government has ordered some 83 Mark 1As. So, what is that most important difference? And it came in all newspapers. Or whatever you are aware of, just tell me. What is the difference between present LCA and Mark 1A? Priya, any idea? Priya, did you get the question? Priya, can you hear me? Sandita, any idea? Uh,
So
difference
probably
between
the Modern usage of avionics.
Yeah, that's true. Okay. Because we can't change the airframe, not the engine. So, what is that one important difference? No, I
So
suggest, yeah.
the
Yeah.
transformation from analog to digitalization of glass cockpits.
That earlier one also, maybe a slight improvement, but the earlier one also was having a glass cockpit, obviously. Almost slightly better one is going to come. But something of more, which is more significant. Okay, I just suggest you people that apart from your coursework, in your own interest, you should be aware of what's happening in the aviation sector, at least within the country and in the neighborhood. Okay, that's how you develop a passion on this subject. Okay, as Sanjita was telling, avionics is one thing which they have improved, and they are gone for something called as AESA and radars. It is actively electronically steered and array radars AESA. What it means is, uh, see, a normal antenna, if you want to rotate, you'll have to rotate it. Let's say you're rotating this in the elevation plane. You'll have to move this mechanical stuff. Okay, physically it has to be moved, which means a lot of power and a lot of inertia also. You can't move it that fast. Now, instead, there is a concept called phased array. What we saw earlier was array. Now, this is phased array. So, instead of just having one antenna, I'll keep multiple antennas, but feed them with different phases. They are all coming from the same source, but then I can always change the phase of the incoming power in such a way that now instead of mechanically moving this beam by moving the reflector, now this beam can be rotated electronically just by changing the phase. There is no mechanical movement of these antennas. Just change the phase, then you can rotate the beam the way you want. So that reduces a lot of weight also, as well as the response is much faster than a mechanical system. Then you will be, what they are also planning is this AESA is going to work like a track while scan radar. So a portion of the radar will keep searching this complete volume. A small portion of it will be, once you detect some target, it will also track that target. So one beam will be for tracking, and the other beam will be for scanning. In fact, what they are telling is they'll track 48 targets simultaneously while scanning. So this is the latest in antenna technology, phased arrays. So something you people will hear about quite a lot in the near future. So that's one of the main improvements of LCA Mark 1A. And apart from that, they have gone for the electronic warfare. Earlier, the generation did not have electronic warfare. You will be surprised to know that what is flying doesn't have electronic warfare pod. So that's there, and some refueling probes have been added, and they're going to use BVR, beyond the visual range missiles. What is that BVR which we are developing now? What India has developed and probably already fitted into the Su-30s? Generally, the fighters they have the short-range missiles, okay, which just works on infrared or at times active OP. But this beyond visual range is actually the AVAX or something will pick up the target and this fellow will just launch it. Approximately what they are aiming is 110 kilometers plus. So even without entering the enemy territory, you can launch these missiles. Uh, the Frenchies have supplied the Meteor. Meteor is very costly system. So you can't afford to buy so many missiles. So we have gone for our indigenous missile. Any idea? What is it called? Okay, just Google it and see. Find out what is that we are trying to uh, develop. Okay, and what is in fact people should go a bit more and see apart from the electronics. What is that propulsion system which is challenging in BVR missiles? The problem with missiles is once you launch, okay, uh, let us say 50 kilometers, end of 50 kilometers, it doesn't have much energy to manual. So if the aircraft is uh, initially it was here at the end of the its maximum range and it has manured in this direction, it really doesn't have that energy to accelerate. Okay, so you can easily dodge these missiles. And that's what happened when these F-16s fired those missiles. The Su-30s were able to take evasive action. They knew that the missiles are coming, so they were able to dodge it. But now there is some propulsion systems which are being developed so that at the fag end of its range, also it can have sufficient energy to carry out such maneuvers. So that's so just find out and see what sort of propulsion system they are using and how is it different from normal propulsion systems of conventional missiles. Okay. Okay, I think I'll end with this. Next class onwards, we'll start with amplifiers, filters, and other components. Okay. Anything you want to ask me? Any doubts on whatever we have covered so far? Sanjita, is it okay?
Yes, sir.
Okay. So please go through the textbook also, okay? And in case you are having any doubts, we can discuss in the next class. Okay then. Thanks, Sanjita. Bye. We'll see you in the next class.
So Priya said that she had some internet issues. That's why she couldn't respond timely.
Nice. Okay, fine. No issues. Just find out
Thank
what is this PVR in the next class and tell me, Sanjita.
Yes. Okay.
And also tell us what is that propulsion system also. What is challenging in it. Okay
Sure.
then. Okay, bye.
Thank you.